Greetings. In this short video, we will discuss primitive roots of a prime number, and I'll provide some examples and also make some comments on primitive roots. So let's start with the definition first. Let P be a prime number. We usually take this prime number to be odd number because there's only one even prime, that's 2. One is a primitive root. You can easily check that once I gave the definition. So really this is useful when you're looking at odd primes, especially large primes. A number R, and this R has to be between 1 and P minus 1, is said to be a primitive root of the prime number P if the following is true. Namely, if you look at the set consisting of R to the power of 1, which is same as R squared, and so on and so forth, R to the power of P minus 1. So really I'm taking first P minus 1 powers of R, this number R, and that set should be equal to 1 to P minus 1. And if that is the case, then we say R is a primitive root of P. And a comment about the set is, by looking at the right hand side, this set has P minus 1 elements, namely 1, 2, 3, up to P minus 1. And here, since we're saying these two sets are exactly same, this must have P minus 1 elements. That means it is not possible for two different powers of R in between 1 and P minus 1 to have the same value. Of course, we compute this mod P. Okay? So no two will yield the same value, mod P, and this set must be equal to that set. In other words, R is somewhere here, we know that. We chose R in between 1 and P minus 1. R squared got to be somewhere here. Different from R. R cubed is different from R and R squared, and so on and so forth. So that such a number is called a primitive root. So here is an example. The example is 3 is a primitive root of the prime number 7. So how do I check this? If I want to check 3 is a primitive root, I got to compute all the powers of 3 up to 6. So 6 powers of 3, and I should get 1 through 6 numbers. Let's check that. You have 3 to the power of 1 is 3. 3 squared is 9, but 9 is congruent to 2 mod 7. 3 cubed is 27. 27 mod 7 is 6. 27 minus 6 is divisible by 7. 3 to the power of 4 is 18, that's 4. mod 7. 3 to the power of 5 is 5 mod 7, and 3 to the power of 6 is congruent to 6 mod 7. In this example, it turns out all the powers of 3, 1 to 6 powers are exactly same as the number, 3 to the power of 6 is 1, sorry, 1. Why 3 to the power, sorry, 3 to the power of 6 is 1. Why is that? This is by Fermat's little theorem. 3 to the power of p minus 1 is congruent to 1 mod 7. So as you could see, all 6 powers of 3 gives you exactly 1 through 6. So let me write that down. So if you look at this list here, 3 to the power of 1, 3 squared, 3 cubed, 3 to the power of 4, and 3 to the power of 5, and 3 to the power of 6, all 6 powers are exactly equal to 1, 2, 3, 4, 5, 6. As you can see, this is 3, 3 squared is 2, 3 cubed is 6, 3 to the power of 4 is 4, 3 to the power of 5 is 5, 3 to the power of 6 is 1. Okay? Therefore, 3 is a primitive root. The question is, do primitive roots exist for any given prime? That's a big result, a profound result. It requires a proof though. If somebody is familiar with field theory, then we could easily prove it, but we're not going to prove that here, so I'm going to state that as a result. So here's the result. The result is theorem. Every prime number has a primitive root. As a matter of fact, it will have many, and there is a number that will tell you how many primitive roots a prime could have, but we're not going to do that, so we're going to assume this. Since we'll be dealing with small primes in this class, you will be able to figure them out quickly by computing different powers of a number and see whether they span the whole list 1 through p minus 1. That's one. A comment I have is, if we have a primitive root, R is a primitive root of P. As I mentioned, R squared, R to the power of P minus 1 would give you the list of numbers 1 through P minus 1. This is exactly the same as 1 through P minus 1. Now, one advantage in writing this way, using a primitive root, is the following. Let's say I take a number, say x here. The x is in between 1 and p minus 1. And I want to compute x inverse mod p. If you want to compute x inverse mod p, you have to, a couple of ways. You could use Fermat's little theorem to compute x inverse, or extended Euclidean algorithm to compute x inverse. But if you write it this way, this x got to be one of these powers of R. Okay, one of these powers of R, if you know the primitive root. So suppose x is R to the power of k. one of the powers here. Then it's easy to find the x inverse. As a matter of fact, you could write down the x inverse. The x inverse would be, what will that be? That is congruent to r to the power of p minus 1 minus k. Okay? Why is that? Because if I multiply these two numbers, I get 1. Why is that? If I multiply r to the power of k times r to the power of p minus 1 minus k, this is r to the power of p minus 1. We know r to the power of p minus 1 is 1. Therefore, this is congruent to 1 mod p. Therefore, find the inverse of an element, if you write in this format, is much easier. You simply subtract p minus, the number from p minus 1. So for example, if p is 7 and r is 3, what is the inverse of 3 squared? Inverse of 3 squared is, according to this, 3 to the power of p minus 1 minus 2. P minus 1 is 4, minus 2, p minus 1 is 6, minus 2 is 3 to the power of 4. So if I multiply 3 squared and 3 to the power of 4, I get 1. Therefore, it's easy to compute the inverses. For example, what's the inverse of 3 to the power of 5? Inverse of 3 to the power of 5 is 3 to the power of 1. Why is that? 5 plus 1 is 6. What's the inverse of 3 cubed? 3 cubed inverse is 3 cubed because 3 cubed times 3 cubed is 3 to the power of 6. So if you write it this way, it's easy to find the inverse. That's one advantage. Okay? In the next video, I'll introduce you the discrete logs, base, primitive root of a prime. Thank you.